Okay, so we're on the back side of notes, talking about dilations, and we have to talk about the properties of a dilation. So they want to know, are the following properties preserved in a dilation? Distance. Are the corresponding sides of the two triangles congruent? So if we measured one of the sides of our triangle before it got dilated and then the same side after it got dilated, is the distance between the points going to stay the same? And the answer is no. All right, your distance is actually going to change. It's either going to get bigger or smaller in a dilation. Angle measure, all the corresponding angles congruent. We talked about that on the front. And we said that if the triangle has to have 180 degrees before and after, the angles are going to have to stay the same. So angle measure is going to stay the same. And so we're going to go ahead and say yes for this one. Okay. A transformation is a change in position, size, shape, or size of a figure. Okay. And remember that a rigid motion, as of right now, before today, all of our transformations were rigid motions. Okay, but now we learned a dilation is a transformation, and we have to remember that rigid motions is a transformation that changes only the position of the figure. Okay, so is a dilation a type of transformation? Yes, because it changes the size. Okay. Is a dilation a type of rigid motion? And the answer here is no. Okay. If you remember, rigid motions preserve two properties. They preserve distance and angle measure. Okay. So is a dilation a type of rigid motion? No. Okay. And the reason is rigid motions preserve distance and angle measure, but dilations do not preserve distance. And because it doesn't preserve both properties, it is not considered a rigid motion. Okay, remember, rigid motion, you're doing a motion, like as in changing the side, so that's fine. But your triangle has to stay rigid, meaning it has to stay the same size and shape. And dilations keep the shape, okay, but not much the size of the shape, okay? And so that's what we have to remember, that dilations are not rigid motions. All right, we got a couple examples here. So number one, what are the coordinates of the image of the point 2, -4 under a dilation centered at the origin with a scale factor of 5, which is how that's read. And so all we have to know is that because we're doing a dilation, this number right here is our scale factor, and with a scale factor, you multiply. So if we have the point 2, -4, we're multiplying both the x and the y by 5, and that's going to give us 10, comma, -20. And there is our dilated point, okay, or the image. Number 2 says find the constant or scale factor for the dilation that maps -4, 6 onto -10, 15. So this is working a little bit backwards. This time they're not telling us what the multiplier is, and we have to figure it out. So how can we get from -4 to -10? But remember, it's a dilation. They're looking for a scale factor. Okay, I could go ahead and subtract 6, but that's not a dilation. It's multiplying. So I have to figure out what number I can multiply -4 by to get to -10. And if you think about it and you kind of guess and check and you say, all right, well, what about 1? Well, that would be -4. If I have a dilation of 2, -4 would become -8. All right, but I have -10. So what if I do a scale factor of 3? That would make it -12. And so what you have to realize is that scale factors don't always have to be whole numbers or integers. It could be something different, like a decimal. And so a real quick trick is that if you don't know what to multiply by, opposite of multiplication is to divide. If I take my new point of -10, or my new x coordinate, okay, and I divide it by the old x coordinate, that's going to tell me the number I multiply by, and that's 2.5 when you divide that, okay? Cool thing is, if you're second guessing yourself, it's got to work for the y's as well. So if I take my new y coordinate and I divide it by my old y coordinate, that should produce the same exact number. All right, and then that way you can have a little bit more confidence of saying that your scale factor, or your k, is 2.5. That's the number you are multiplying by, okay? Meaning that your sides in your triangle or your figure are getting 2.5 times bigger than what they used to be. Okay. Number 3, it says find the coordinates of the image of each point under the given composition of transformation. So remember in a composition that if they use this notation with the open circle, that open circle means following. And that in a composition, the second transformation always comes first. Okay, so this is what we're going to do first. So we're going to take -2, -5, and the grid is here. It's optional. It doesn't say that we have to graph. And for dilations, I don't really graph. I just use the multiplier. All right. So our scale factor is 2, which means we are going to go ahead and multiply both our x and our y by 2. And so our point is going to change to -4, -10. Okay. The composition, remember, you never go back to the original. You apply it to the point that you just got. All right. And so in a translation, you could use the graph. The -6 is 6 to the left. Remember, left and right number comes first, and then 3 up. Okay, so I could use the graph, or I like to just put the little -6 underneath the x and a little +3 underneath the y. And that is going to go ahead and give me -10, -7. And there is my final coordinate. And that one is my answer. Okay, let's go ahead and do the next one. So again, remember, second transformation is always done first. And for rotations, we're going to have to make sure that we use our graph, all right? Because we actually turn our paper to graph it and get our new coordinates. So our current point is at -9, +6. So it's right here, all right? Remember, a rotation of 90 degrees should put it into this quadrant. So let's go ahead and take the top of our paper. The right way to turn your paper is to the right. So turn your paper once to the right. And now we're going to go ahead and regraph -9, +6. And it ends up right here. Okay, so I'm going to circle it. And so when I turn my paper back, now I can go ahead and state my coordinates of that point. And notice it did hop into the next quadrant. So that is exactly where I wanted it to go. So I know I did it right. And we are now at -6, -9. Okay, and so now we're going to go ahead and do our second transformation, which is a dilation, and we have to do it on that point. Notice our scale factor is 1/3, and so you'll be multiplying by 1/3. All right, totally use your calculator if you need to. You can also use this little hint that multiplying by 1/3 is the same thing as dividing by 3, if that makes things any easier. So 1/3 of -6 is -2, and 1/3 of -9, or 1/3 times -9, whichever way you want to think about it, is -3. And there is our final coordinate, and so that one is our answer. Okay, let's take a look at number 4. Number 4, this one does say graph. Okay, so we're going to go ahead and graph triangle hen, who's at 0, 4, 6, 4, and 4, -2. All right, part A says graph and state the coordinates of triangle H prime, E prime, N prime, the image of triangle hen under a dilation of a half centered at the origin. So because we're centered at the origin, all we have to do is take that scale factor of a half and multiply all of our coordinates by a half. So this is going to get multiplied by a half, 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 multiplied by a half. Dilations are very simple as long as you remember to multiply by the scale factor. All right, 0 times a half. Well, when you multiply 0 by anything, it turns to stay 0. Okay, 4 times a half, or half of 4, is 2. 6 times a half, or half of 6, is 3. 4 times a half is 2. 4 times a half is 2. And -2 times a half is -1. And so now if I go ahead and graph those, 0, 2 is here, and that's H prime. 3, 2 is here, which is E prime. And 2, -1 is here, and that's N prime. So notice what happened to our triangle. It got smaller. It also got closer to the center of our dilation, which is the origin. Okay. So now in part B, they want us to find the lengths of HE. And since HE is a horizontal line segment, all you have to do is count blocks. So that's 1, 2, 3, 4, 5, 6 units long. And now if I count H prime to E prime, which is also a horizontal line segment, 1, 2, 3. So notice what happened. You had an original segment with a length of 6. A dilation of a half made it half as big. Half of 6 is 3. They want us to find the ratio of HE to H prime E prime. So a ratio is very easy. All we have to do is replace HE with the length, which is 6, add in our colon, and then replace H prime E prime with the length of 3. And that's a good ratio, except ratios are always reduced. So think of it as like a fraction. What number can you divide 6 and 3 by? Okay, that goes into both of them. And the answer is 3. So if I divide 6 by 3, we end up with 2. And 3 divided by 3 is 1. So 6 to 3 reduces to a ratio of 2 to 1. Okay. Part D says find the areas of triangle. I don't know if you guys remember your triangle area formula. Good news, it's on our reference sheet. So the area of a triangle is 1/2 base times height. And remember that a height has to be a perpendicular to your base in order to be considered a height. Okay, so let's go ahead and use our formula for our big triangle. I think HE would make a great base. We'll use this as our base. And then our height is going to come from the opposite vertice, which is N, and go perpendicular to that base. See that perpendicular upside down symbol? So that's how we know we did it right. And now we just need the lengths. So the length of that base, which we used HE, we already counted, is 6. And the height that goes from N to that base, perpendicular, is 1, 2, 3, 4, 5, 6 as well. All right, half times 6 times 6, or I like to do 6 times 6, which is 36, and then take half. Either way, you get 18. All right, so triangle HEN has an area of 18 units squared. Area is always labeled in units squared. Okay. If I go to the little triangle now, we're going to use H prime E prime as the base, and so our new base is going to be 3. Okay. And our height's going to go from N perpendicular to that base, and you can see that that is also 3. Remember, all the line segments follow that scale factor. Okay. But now this time, half times 3 times 3, 3 times 3 is 9, and half of 9 is 4.5. And so a triangle H prime, E prime, N prime has an area of 4.5 units squared. A lot of people would have thought it would have been 9 units squared because the original was 18 and half of 18 is 9. But area doesn't follow that same scale factor, if you notice. All the line segments do, but it makes the area not. So the ratio of the areas is 18 to 4.5, which is an okay ratio, but ratios always need to be reduced. And if you reduce that, 4.5 goes into 18 4 times. So it's a 4-to-1 ratio. Okay. What happens is that with area, because it's labeled in units squared, you take your scale factor and you square it, you would get 1/4. And so you can say that the area is 1/4. Area is 1/4 the size of the original. Okay. All right. And so that is all we have today. I will see you guys on the next day of notes.